Okay, so hi everyone. My name is Nick Karstinos. I'm a PhD student at the University of Athens, working with Professor Dimitris Gizopoulos. And today I'm going to be presenting with you the work we did with my colleague George Marios Pagoulis, who is also a PhD student at the University of Athens. And basically what we've been doing is we tried to implement the RISC V Hypervisor Extension and actually get it working inside the gem5 simulator. So let's start off with some basic background about RISC V. Most of you might be familiar with all this, but I'll say them anyway. So in RISC V, we have modularity by default in the ISA. And what does this mean? This means that the designers actually carved out the base ISA, which gives you the essence of computation. So you get basic integer arithmetic, you get control flow constructs, and you get memory operations, so loads and stores. And then if you want something more out of your processor, if you want specialized instructions, you have to opt into ISA extensions, which are bags of semantically similar or domain-specific instructions that provide you with additional functionality. And each extension is represented by a capital English letter. So you have the A extension for atomic instructions, you have the B extension for bit manipulation instructions. You get the idea. And a natural question is, why would you want this modular design in the RISC V ISA? And the answer is, what we gain is that when we design hardware and implement it, we only implement what we actually need. That's what you get out of the modularity of the ISA. So what you can do is you can tailor the hardware to the application. And your hardware's complexity will be roughly analogous to the complexity of the ISA extensions that you need. If you have minimal needs from the ISA, so if you're building a simple embedded processor and you just need the base ISA, then your design will be much simpler, your hardware will be much simpler, and that will probably make you happy because that's easy to test, easy to verify. Okay, so that's the idea of extensions. Let's talk a bit about the RISC V H extension, which is the hypervisor extension. So what would you need this for? The idea here is that we want to host a guest operating system. So you want to have VMs. And the H extension allows you to do this efficiently because there are other methods of hosting a guest OS, like trap and emulate and some other stuff. But the H extension gives you all the utilities to do this really, really efficiently, and you actually need this. What's essentially being done is that the whole supervisor level architecture is being virtualized. So the basic parts in the RISC-V ISA extension is the new registers that you have to manage the hypervisor and the VM state, as well as the page walking and many other things. So you have 26 new CSRs. You also get a lot of new interrupts and exceptions for the guest. The big thing is that you get the two-stage translation. You actually get a new type of page walk called the G-stage walk, which allows you to turn guest physical addresses, which are host virtual, to host physical addresses. And finally, you get some special hypervisor instructions that the hypervisor uses to perform some special memory accesses and some memory fences. So the good news is that H extension is now slowly being pulled into gem5. So the pull request is merged onto the staging branch of version 25. So currently the implementation only supports the atomic CPU, but we're extending the implementation right now to also work with the timing CPU models. And we will upstream this support as well when our development efforts reach a stable point. And in this talk, I'm hoping to give you a high-level overview of the implementation and a small demo with the video. that we have. So as we said, the implementation semantically consists of these four big parts. You have the registers, the interrupts, the two-stage translation, and the instructions. So because we have limited time, I'm not going to go into all the bit fields of the new registers, what they do, how you write them, what are the read and write masks, and all these things. I'm just going to give you an example of something we have to do with registers in a virtualized environment. So imagine the following scenario. You have your Linux OS, and in the top of the picture, Linux runs natively, so in supervisor mode. There is no hypervisor. Whereas in the bottom, Linux runs in virtual supervisor mode, so we have a guest OS. So imagine that the OS wants to read the supervisor status register. How would you do that? You issue this instruction, CSR read, for the status register. The hardware says, OK, I'm going to execute the instruction. You have permissions. It's the CSR access is not going to crash, and you get back the value of a status. So what about the bottom image, however? Because in the bottom image, it's a guest OS. So remember that an OS that's being virtualized is unchanged. So the OS's code is exactly the same in both cases. So in the bottom case, again, because we have an unmodified OS that is being virtualized, it's going to issue the exact same instruction. And we just have to play a trick on it and make it think that it's reading a status. But in hardware, inside gem5, what we're going to do is that we're actually going to give it the virtual supervisor register, VS status, because the S status register is now managed by the hypervisor. And you don't want to give the hypervisor's CSR to the guest OS. And this is a trick that the hardware, gem5, plays transparently to the OS that's being virtualized. Okay, so that's a neat thing about registers. Let's move on to interrupts and exceptions. The picture here is not too complicated. You just have some new fault types. You basically have new interrupts for the guest. You also have guest page faults, whereas previously you only had normal page faults. Now you have them for the guest as well. You also have virtual environment calls and some other things. And what you have to do is you have to extend the fault handling logic in gem5 to accommodate for these new types of faults and these new privileges. Because these new privileges that appear in the H extension, two of them are the hypervisor mode, HS, and another one is the virtual supervisor mode, can also handle and delegate faults. So you have to extend the fault handling to accommodate for all of this. And now let's move on to the, let's say, the beef, the main part of the implementation, which is the two-stage translation, where you have to implement the G-stage walk. So imagine we have a normal page walk, as we all know. This is a three-level page table. You have the SATP register that contains the base of the level 0 page table. And what do? You split your virtual address into three parts for a three-level page table, and then you index with each part the corresponding level in the page table. And as you move along, you finally reach your data page, at which point you apply your offset and get the data. So this is how page walking would work without the H extension. But in H extension, if we include it, and if the guest OS runs, we can actually do what's called a two-stage translation. So the first stage, now called the VS stage, is exactly the same as the picture we showed just before. But there's a catch here. And what's the catch? That every address that's purple here is a guest physical address. The guest thinks that it has a physical address at that point. But actually, from the host point of view, this is again a virtual address. So what this stage is here for is it's here to turn every purple address into an actual physical address for the host, which is yellow. So in the top, you have the normal page walk that you know of. And the only catch is every time you encounter something purple, you pass it through G states to actually get a physical address in RAM. So the translation would work kind of like this. You first get the page register in the top stage. Because it's purple, you have to pass it through the full G states to get an actual address in RAM to find the level 0 guests page table entry. And then you go on in the same way. So for each step in the upper table, you have to do a full sweep of the G states. Finally, you get to your data in the same way and you return it. So that's the two-stage translation. Finally, you have to implement the hypervisor instructions. That's not too tricky to do. It's just some new fancies and some special loads and stores. You just have to extend the ISA specification files with these instruction implementations, basically. We also had to define some memory instruction formats for the hypervisor loads and stores, but that's just specific to the way that gem5 does things. It's not something to do with the H extension. So how do you validate this? The first thing we did was running some public tests that verify the H extension. So you have tests for registers, you have tests for the new exceptions and interrupts. HLV and HSV are the hypervisor special loads and stores, and then some tests for two-stage translation. After we gained confidence that we had the passing status on these tests, you actually have to do the hard step and try to run a hypervisor which will manage a guest virtual machine. And if the guest's virtual machine operating system boots up and can actually execute programs without problems, you would gain pretty strong confidence in the correctness of your implementation. So in our case, we chose to run Xvisor, which is a type 1 or bare metal hypervisor. Okay, so at this point, I'm going to stop and briefly show you the video that shows a boot of Xvisor. But I'm just going to say that because of the limited time, my descriptions were pretty contrived of details. So if you want some more details, we have a CARV24 paper that gives some more details because I only had time to give some basic examples. Okay, so I'm going to try to go to the video now and briefly show that. Okay. Okay, so before I let it play, on the left terminal, you can see the invocation of the gem5 simulation. And on the right terminal, we will attach to the terminal to actually see what the simulated system is doing. So the first thing that's going to be done is that the OpenSBI firmware boots runs, and what it will do, okay, let me give a few more details. So we give the firmware, and as a kernel, we pass in the hypervisor, the Xvisor's binary, because that's the kernel essentially. And then we pass in a disk as well. So what's going to happen is that the OpenSBI firmware runs. It's gonna after it's done its work, it's gonna pass the ball to Xvisor. All these messages prefixed by init are Xvisor's initialization. At this point, Xvisor is trying to create a guest. So it has, we have already provided Xvisor with the guest 0 configuration. And right now it's loading the guest's firmware, the guest's OS, and the guest disk image in memory so that they are ready and we can start the guest right after. So when this loading finishes, we're gonna drop to a prompt inside Xvisor, which should happen right about now, I think. Okay, is it playing? It's playing. Oh, come on. Okay, there's the prompt. So this is the Xvisor prompt. And now the guest is ready to be started. So how do you start the jest? You issue the kick command. You say kick the jest 0. So start the jest 0. At this point, both things are running. There's a thread running that's the hypervisor thread, and you also have the jest thread. But the jest has only run its firmware now, and what we're doing with this command is that we're binding to the emulated terminal in the jest. So all these messages now prefixed by jest and then jest 0, UART 0 are actually inside the jest. The basic firmware has just loaded, and by issuing the autoexec command, we're copying the OS into memory, and we're also, I think, copying the disk as well into memory. And then, after all that is done, the basic firmware is gonna jump into the guest Linux, which happened right now. So right now you can see a normal Linux boot that you have seen 1,000 times, but it's in the guest. So the firmware loaded Xvisor, Xvisor prepared the guest, we started the guest, and then the guest firmware loaded the OS into memory and actually booted Linux. And finally, when this boot finishes, at some point, I hope, we're going to get a prompt inside the guest operating system, and then we can run some commands just to see that the virtual user mode is also working. Okay, so I think it's finished now, and we're just going to issue a list command, I think. Yeah, and we'll get a display of the contents of the directory. Yep, it's the ls command, and we run this. Yep, and we get the contents. So yeah, that's the short demo. Wish I had some more time to actually show you a live demo as well, but yeah, I think I'm gonna end here and pass it on for questions. Okay, so thank you very much.
Questions for Nick? And by the way, the 25 was 25.0 was released, so it's in the stable.
Ooh, okay, nice. I didn't know that.
I have a question about the interrupt. So I know there is a maybe not new, but a new specification about interrupt, which is AIA, right?
You're talking about AIA, advanced interrupt.
Yeah.
Yeah, I don't think we've looked into that. Yeah, because it's pretty new. So what we support, I think, is the base.
Yeah, I understand it.
Yeah.
And there is another question about how about the interrupt license, the interrupt latency.
Latency.
Yeah.
So do you mean if we have measurements regarding
Are you ever measuring some performance latency, something else?
There are some measurements that I can refer you to in the paper. So this paper has some measurements, but I'm not sure that we've measured exactly what you're asking for.
Yeah.
So are you asking how long does it take to handle an interrupt in the gem5 code? Or how long does the software running think that like how much time has passed before gem5 actually handles the interrupt?
Are you measure that?
Yeah. I don't think we have measurements of that.
Okay.
Yeah.
Okay. So
but it should be completely measurable.
Yeah,
The infrastructure is there.
Something evaluate.
Yeah, for sure.
Yeah, I understand, because I have also do something about the virtualization, CPU virtualization. So maybe we talk it later about.
Okay, yeah, for sure. I'd be happy to. Yeah.
Thank you very much for presentation.
Thank you.
Any other questions? Great. Thanks so much, Matt.
Okay.